Today we'll be discussing Activeloop Hub with Davit Buniatyan, who is one of the creators of Activeloop Hub. Davit, thanks for coming on the show.
Thanks, Aaron. Thanks for having me.
So maybe you can start us off by explaining, there's lots to discuss here, and I'm excited to get into all of it. But first, introduce Activeloop Hub to our listeners, Davit, if you would.
Mm-hmm. So Activeloop Hub is a dataset format for AI applications. The vision is to become a database for AI. And currently it's more legally speaking or technically speaking, it's more like a data store for deep learning applications. So the main goal behind the scenes is that you have all these data formats for tabular data like Parquet. You have databases, you have data warehouses, data lakes, and now so-called lake houses. But you don't have one for specialized, especially deep learning applications. And over the past 10 years, we have seen this huge growth with applications of neural networks in unstructured data or complex data with images, video, audio. But still, data scientists, they operate on top of this data as they are files on your desktop, or they are objects or blobs on object storage. So that's what we are trying to change here, is to provide unified format access for data scientists to work with large-scale datasets when they are operating on top of deep learning applications.
Got it. And that was a useful clarification at the beginning that, it aspires to be a database for images. Today, it's more like a data store. And does that imply that with time you might add more database-like functionality?
Yes. So as we have seen, like there's a lot of, like when you mention a database, it comes with a huge lot of expectations on how the data should be reached and / accessed. But a lot of those expectations are not there yet for deep learning practitioners. So, for example, like ACID transactions or making consistency as like part of the ACID across multiple like writers. Like a lot of times, like the order is not important when you are training those models. Even further, like for example, in a training process, you will expect the data to be in a shuffled manner or like come in a random order manner, so you can train your models best. So the expectations or the use cases are slightly different. That gives you a discount on like how to call or how to frame the tool itself that can be helpful for processing the data.
You compared it to Parquet, and when people are using Parquet, sometimes they refer to their storage as a data lake. Could you call this a data lake for computer vision?
Yes, that's also a very good like synonym for what we are doing.
Good. And then I guess one other aspect I'm curious about, and then we'll get into how this all began. But you also said that most people are the kind of traditional way is to download files locally to your computer and then operate them as you're going through training exercises or testing inference. This prevents the need for downloading locally. Then you work. You're able to take the traditional tooling and kind of connect it to this cloud store, a cloud data lake. Is that the idea? And so you do your kind of TensorFlow, if you will, or PyTorch, and it accesses Activeloop directly. Activeloop, sorry.
Yes, let me try to give you a kind of a example how it works. Let's say you have 1,000,000 images, and you have also 1,000,000 labels. And those labels are, take the most simplest case where it's like dog or cat trying to, and you are trying to build a model that will classify if this is an image with the dogs or cats. The way usually people operate now is that they write this 100 lines of boilerplate code to parse the folder structure if it's locally on the machine. If it's remotely, then you have to actually do copy to your local machine and then start doing the process. Imagine if either this data grows huge, or instead of having a single node, you can also like do multi-GPU training, like distributed training, where you have to run on these multiple machines, or you do like instead of a training or inference on 100 GPUs. Every time you start a virtual machine on the cloud, or like open your Jupyter notebook on your local machine, you have to go and copy the data from the centralized source to your machine. So now what we do differently is, first of all, instead of treating this 1 million as single files, we actually, like as images or labels, we treat them as tensors or columns in our, like, let's say call it data set. You have multiple columns. Each column for us, instead of being a one-dimensional array, it's now n-dimensional array or tensor. So now your data set becomes, you have image tensor and label tensor. An image tensor has the shape of 1 million by 512 by 512 by 3, and label tensor is 1 million by 1. And deep learning simply becomes learning a function from image tensor to label tensor. And you can either connect this to PyTorch or TensorFlow. And instead of now actually copying the data gets streamed over the network to your models directly. So it doesn't get cached on the local disk, and you can save a lot of time while you are processing this dataset. So, and what we do behind the scenes, like where the core value comes into this place, is that we take this 1 million by 512 by 512 by 3 huge array, and this is not huge. This is like a small huge, basically a data set. And we chunk the data and lay out on top of an object storage like S3 on AWS, such that when you stream the data from S3 to a virtual machine, for the GPUs or for the models when they're doing the training process, they feel the data is actually local to the machine. So which means that now your model being limited to let's say 1 terabyte of your local disk, it can have access to a petabyte scale data set sitting on top of S3. And instead of you running a single machine, now you can have a workload of 1,000 machines. So it's very similar to how, let's say, MapReduce or like Spark will operate on top of this data, but with nuances or with the considerations especially for deep learning applications. And one of those considerations is that when you are running a compute in machine learning, like deep learning models, they don't care what the data is in / out. It's a tensor in and tensor out. And then you have the architecture behind the scenes. Obviously, this architecture is biased on type of the data it's accepting. But even so, like with recent transformer models, it's becoming kind of universal. So our goal, or as like the goal of the hub, is to prepare the data, lay out the data on a remote storage, and then transfer over the network to the model as simple from the model perspective as possible. Because we were before storing the data as like, what is the best way for humans to store the data? But now we are can we actually optimize this? Because we know how the data sets are operated, how they're going to be computed with deep learning applications. Now we can backtrack and say, okay, what will be the best way to store this data on a local or remote storage? And then how to move it over the network through the caches and then bring it to the machine. And once you also know, like the big difference, let's call it also another difference, like people can use distributed file systems, or they can use like a remote way of accessing this data. But one thing that these file systems or like operating system level doesn't know is how this data is going to be computed. Like what is the future looks like when, like, what is the next 10 elements, how I'm going to compute. And if you can incorporate this to the way you are both storing and then transferring this data over the network, then you can actually guarantee performance and speed for your machine learning models.
Yeah, totally. And maybe to extend this conversation just a little bit, one of the principles that I think as an industry we've kind of agreed is important is that you want to process the data the same in training as you do in production and inference. The data is prepared. And I know that's really important when you're doing lots of data transformations like you would with numerical or tabular data. It's probably less critical with images, although maybe there's some processing. But at least at a minimum, what you're doing is making you're bringing training to the cloud where production is going to happen anyway, and then or inference is going to happen. Do you also are there benefits in the pre-processing of images that you have a similar processing environment the way I'm describing, or is that not as important given there's probably less processing on images?
No, it's actually one of the considerations. When is the right time to do the pre-processing of the data / how to do that? So let's take the training example. When you get arbitrary size images, when you give it input to the model, you actually have to resize and normalize the data before feeding it to the model. Otherwise, your model will not learn very well. And then there's a consideration, okay, when is the right time to do this pre-processing? Should I do it actually on the remote storage? And what you can do recently using the new APIs or like S3 or using Lambda functions? Or can you actually do it on the CPU while your GPU is running the computation? Furthermore, like with unstructured data, like decompression actually becomes a big bottleneck. And you might think that the network is the bottleneck or the pre-processing is the bottleneck, but actually decompressing the data, I don't know, like take the most simple example, you have PNG file format, and then you're bringing it to the tensorized form where you have to like fully decompress. That becomes the bottleneck. So what Hub is doing behind the scenes on behalf of the data scientist is that it does all this tweaks. Okay, when should I move? Like, how should I move the data? When should I decompress? Where should I put it into the cache? How do I should take this from the cache and then apply the pre-processing function that the user defined, and then how I should fit this into the machine learning models. So we try to make the data scientist life as easy as possible, and then give them like you can think of it as a data lake access for their data sets.
Got it. No, okay. I think I follow. This is good. And Davit, let's take some time to talk about how you got to this. Presumably, this was like a personal problem of yours, and maybe you can talk to us how you encountered this problem and then discovered that it was kind of a broad problem.
Mm-hmm. I wouldn't call it was a personal. So before starting the company, I was doing a PhD at Princeton University. Actually, just fun story. When I got into Princeton, I got into an advisor, a professor there interviewed me, like accepted me to a computer vision lab. I was so excited to come there. And apparently when I got there, he left to Bay Area to start his own self-driving car company. So I had to find another professor because I didn't want him to join a startup at that point. He did offer me. And I accidentally or incidentally got into this neuroscience lab led by Sebastian Son, who is working on this field called connectomics. And connectomics is a new branch in neuroscience. I'm not sure if you've heard of. It tries to reconstruct the connectivity of neurons inside the brain. So what we were doing more specifically, we were taking a mouse brain, a 1 millimeter volume of it, cutting into very thin slices. Each slice was at nano resolution. So each slice was 100,000 by 100,000 pixels, and we had 20,000 of those slices per sample. So the data set size was getting to petabyte scale data. And what we had to do is we had to take this data and then use deep learning or artificial neural networks to be able to segment the neurons, find the connections, build the graph. So later neuroscientists can do research to understand how the brain works. What are the naturally, like biologically inspired real algorithms? Because all the neural network stuff that you see today is actually based on 50 years ago understanding of how the neurons or how the brain works. And there's a lot has been changed. Like, for example, one interesting thing you can prove out is that backpropagation doesn't exist inside the brain. Like, that's an algorithm that is used widely in PyTorch or TensorFlow to train those models. So I was not doing the neuroscience part. I was mostly involved with the infrastructure and training those models. And the problem that we had is that processing a petabyte scale data at least 5 years ago on the cloud was super painful. Kubernetes was not scaling to that point. Like, we tried Airflow, it was hardly working for distributing the tasks. The data, to be able to optimize the cost from, I think, the order of millions to 5 times cheaper, we had to rethink how the data should be stored on those machines, how it should be streamed over the network from the machine to run the CPU or the inference. At some cases, actually, for some certain models, it is much cheaper to run. If you compile it pretty well on CPUs, it's much cheaper to run on the CPUs rather than on GPUs, even though it's slower, but then you can scale. It's actually 30% cheaper. And then you do all these optimizations. You understand that all the tooling you have for traditional analytical workloads, like you have Snowflakes, you have Databricks, they are not you can't use them there. You have a bunch of other, all the work that has been done over the past 20 years for big data is unusable in this, I'll call it unstructured space or complicated data space. Here it was a 4-dimensional data. So, and a huge data set. And we had to rethink all these tools, and those problems actually and the insights that we learned there appear to be not only inside our lab, but also in other labs, not necessarily in biomedical applications. And apparently when we started the company 3 years ago, got into Y Combinator, it appeared it's actually not only in our research community, but it's also getting into the industry and startups and also large companies that we have seen how being used.
That's fantastic. So it's just to clarify some of those points. So you were going to a computer vision lab originally, and then that didn't work out, and you ended up in like a neurology lab, I suppose. But this led to you kind of, I had that not happened, you might not have kind of had these same insights that into how neural networks operate, and then how to operate them at scale, that led you back to doing computer vision.
Definitely, it's super interesting. And I find today, like self-driving car companies, some of them, I will not open the brackets, they have the exact issue for storing this data at scale, like when they are already on petabyte scale
Yeah.
data sets that we had in the lab like 5 years ago. Like exactly the same problems. And they are still struggling coming up with third version or fourth version of their format to be able to store this data and then also visualize this data. Visualization is another world. So this is very interesting, and I don't know. And one thing is interesting as well. Actually, our lab was one of the first, not one of the first folks that used. There's a famous like neural network architecture called convolutional neural networks. Because of that, started the revolution of the deep learning around 10 years ago. They actually started using those neural nets in 2008, where no one was using yet, for doing all the segmentation work. And all the revolution actually started after Alex Krzyzewski did the AlexNet that used convolutional nets for doing the classification of ImageNet dataset. So they were like behind, like or I'll say behind, also like away ahead of it, like 4 years ago or 5 years ago. So yeah, that's pretty interesting actually. And you can find a lot of like, I'll say golden pieces in all these research labs. They're like tracked on solving a totally different problem, but the problem that they are solving on the way can actually unlock other use cases in totally independent industries.
And you didn't, you mentioned you didn't want to join a startup when you joined university for the PhD, but I suppose at some point during this project you decided that this could be a company or it could be an open source project. When did that happen, and what led you to think that?
Yeah, the problem that we had is that actually like this was super expensive to run this computation on the cloud. And we're like wondering, why do we have to pay so much amount of money to the cloud to be able to execute this? And especially when you're in research lab, even though that project was super well funded by the government, like we have to be very, very lean on how this like each like cent is used on the computation. So we have to do all this back work and computation very well. And of course, like we are PhD students, so we were messing up and we had to rerun the whole computation from the middle. And that was like just increasing the infrastructure cost there. And at that point, it's like, okay, why don't we try and see if this could be interesting, let's say for Y Combinator. And that's how we applied. We initially thought, okay, yeah, we will get in, we'll see how it goes. So we'll finish our PhDs because we want to become like professors, academics, and so on. And then we got into YC. It's like, yeah, let's give it a try. It will be a cool internship. And once you're here, you're like, okay, wow, that's like so many opportunities where you can give a try and try to solve. And at some point when, like, unfortunately last year, I took a leave of absence from the university. So last year I dropped, like, because they gave me 3 years, were super kind, super thankful. They helped me a lot on this journey. And unfortunately they gave me like, hey, you decide now, either you're coming back or you're continuing. And apparently, and this is on the topic for this conversation, if you're doing an open source and a startup, and like I had this in my head, is like I can have much bigger impact on computer science while building the company than actually do the research and try to come up with an academic paper that could be useful in other sense. So eventually you make this one of those decisions that you're going to always regret. Doesn't matter what. You choose to start continue a company or doing the company, or you go and finish your PhD. I wish I was at the point where I graduated already and then started the company, but like my advisor and like I think another professor at Princeton, who is also now like CTO of Timescale DB, he gave me this advice saying that, hey, like you can do both. You can do both at the same time. There's no problem with that. But you won't succeed in either of them. So you have to focus and choose one and try to be best at it. And that's kind of I was trying to operate on these principles so far.
Well, I think a lot of us are pretty excited that you chose to pursue the company and the project. Well, having a research paper from you would be nice, but there's 4,000 GitHub stars that are excited to have the code you've produced. So appreciate that. Great. So, going into YC, were there a lot of other PhDs in YC, or how common or uncommon is that?
Well, there were a few PhDs. Like I remember in biotech or in deep tech, especially, like folks who were doing deep tech startups. There are a few. But then I have seen more actually non-PhDs or slash non like academically coming from the background to actually doing open source, which is more interesting. Like so, basically, open source. There's no any ground for like barrier for you to start a project on the open source, and if it gets successful, then you can actually build a company on top. So to be fair, when we started, we had an open source solution, but that was not Hub. So Hub actually came like a year later after we have been iterating with customers and learning about their problems. So on our side, just to give some side off here, so when we started working with companies, we then afterwards we connected the dots. Wait, here they are actually storing their data inefficiently. Like we had one customer had 80 million text documents, and they were storing this document txt by txt on S3, which is very inefficient if you want to move the data. It's like you have to copy file by file, and like tiny files is super bad. And it's like, wait, why are they doing that? Then we worked with another company who had like really huge aerial imaging, like petabyte scale data on S3, and then totally different space, so not documents. And they were storing this like with a 20 years old way of how the whole community of aerial imaging processing has been storing this data. And then we said, okay, why don't they have much better way of like they can save on 30% on their compression if they don't use the same compression they do. With the NLPs, like they don't even were saving it in any compression. They were like just also operating on single files. So those kind of problems we actually learned while we were working with customers. So we haven't started the open source before starting the company, but there are a lot of companies, especially now, that get into Y Combinator that start their open source before they, like in the previous company, they see how this gets useful across their previous company, or they come from the research as well. But then YC has been mostly, when I joined, they have been mostly focused on like SaaS B2B slash B2C companies. And then they were doing this transition to become less consumer to more enterprise, like the selection process, as far as I've noticed. So that's just my humble opinion here. Yeah, that was kind of the story there.
And earlier you mentioned that there were this is a need in not just computer vision, but also NLP with audio files. And you mentioned some text documents, but you've focused on computer vision, right? Like is there could I use this on audio files, or would this not work?
So the thing is that you can use this for audio files. You can use this for TXT files. You can even use it for tabular data, like instead of using Parquet. But we have we have to pick a battle. You have to focus on something, try to be the best there. And we focus on images and computer vision applications. So obviously, as the time goes and we had more resources, we can go and back and start optimizing for other scapes, other like data modalities. But especially with computer vision, you actually have to support all the data modalities. It's just since the bottleneck is on the images, you have to actually solve the bottleneck. So that's where we put our first like flag, essentially saying, okay, let us focus on this imaging, videos especially, and try to make it as good as possible for others to train and deploy their models on top. So we are optimized or first for images, but then you also do support other data modalities, and we're going to expand the data modalities given the customer slash user community member feedback.
Going back to when you said you were talking to these companies and you discovered they had these other issues and needs, and you changed the product. It sounded like you had kind of a new open source like hub kind of emerged from those learnings. Was that scary at all to feel like, oh, we built one thing, but we really should have built hub, a new thing, and yeah, I guess was talk to us about like kind of the emotions and the process of kind of discovering the need for hub.
We went through a lot. So that changing that product was not the most scariest thing, to be honest, through that journey. So there are a lot of like problems and stress and like a lot of issues that you face as a founder while you're building a company, and especially if you are doing in deep tech, that's even further makes the problem much more trickier. And let me explain you why. Like the way I call like or define a product market fit is when you build a company that's, I'll get into the nerdy stuff, like that's, your company is basically end-to-end differentiable. And it's very similar to neural networks or deep learning, how you train those models. So you can actually do certain actions and then increase your growth metrics, what you're targeting for. Unless you do that, you as a founder, your goal is to do all these Bayesian experiments or run experiments to figure out, should you explore further or should you try to exploit further? And explore further is try another product or try another feature. And exploit is like, let me double down on this and try to see if I can go further. So until you have this PMF, then you are doing all this exploration work. So at some point and our initial product, to be honest, like it worked pretty well. So initially what we have deployed was a software and the cloud alternative for you to run computation on crypto mining GPUs on distributed scale, which was 10 times cheaper than you rent a GPU on AWS. So we built that. We got actually order of 1,000 users, I think, during the first month. And we got struggling. We were like struggling on the GPU access. We had an order of, I think, hundreds to up to 1,000 GPUs available, and all of them were just fully utilized. But the problem, what we learned from enterprises is that their data, they won't trust us in any time near soon, even if we do all the best encryption, whatever there is possible to do, to move their data to these crypto mining farms. And then it's like, okay, if we can't help those companies, then it's super difficult for us to build a meaningful business on top of the usage that we got, even though we got a lot of usage. So we started then working closely with those companies to understand what are their real needs and what are the problems they are facing at the moment. And apparently data was one of them. You might have thought at that point that it's already a solved problem by all these traditional players in the field and huge giants in the field.
Awesome. So take us to where you go from here. So you've now got Hub. It's quite popular. I think we saw that it was like one of the GitHub trending Python projects. You got a bunch of community members. You found customers. What are the kind of goals for the project that is kind of an open source user I can look forward to, or the kind of the vision from here?
So for open source user especially, what we are pushing so far is take from if you have a spectrum of on one end you have a format, we are going to push it till the database solution and add all this like databasey features while the deep learning community is also like is maturing. Basically their needs becoming more mature, more exact. Instead of each company having their own like different needs, they become normalized. So that's what we promise on the open source side of things. And on the platform, we recently launched the managed version of our hub, which also includes not only just storing this data where you can upload to our managed service, or you can upload to your own S3 or GCS managed by us. We also help you to visualize these datasets at scale on your browser and be able to run version control and analytics to understand how the data, and then integrate easily with PyTorch or TensorFlow to train those models. So that's on our like roadmap, is to actually take the open source, validate this is useful for companies/enterprise to be used, and then double down on the growth of both the platform and the open source.
That's awesome. The database vision is exciting. To help me understand how that fits with inference. So it makes sense to me in training. I can imagine a big database, and I can write a script that connects the database to my model training environment. If I then want to take that model and deploy it on a video stream, for example, where does the database come in, or does it? Would I save frames or images to the database, or just on occasion for future training?
So yes, so if you're running a real-time inference, I wouldn't say you need Hub. You can just directly pass the data from an incoming stream to your model and run the inference. But if you are also like storing this data, as you mentioned, or you're also storing the predictions of your data, and then you want to do backtracking at the later, once you get a new model to be able to run this data set, then you have to store it in somehow. Like for example, like a company might have 80 different models. They're constantly training, retraining, making sure, or let's say you want to be compliant. Your model you trained on 100 million users, and then there's like thousands of users no longer want their data to be with your platform. You have to go and retrain your model by removing this data. And then you have to run the inference back again, whatever the other users had. So there's a lot you have to do, especially with storing these data sets, to be compliant, and also run the inference. Like inference is also a key part, like batched inference. I'll call this in this manner. For real-time inference, you might not need help at this point of the time.
Yeah, makes sense. And then you've kind of on your website you list some areas of focus, which are kind of the areas where we're seeing a lot of computer vision used. Do you find that those are, that the product lends itself to? You talked about autonomous driving earlier. We know that medical images is a popular place. Drone or aerial, I think, came up in our discussion already. Yeah, are there certain areas where you feel like this is a particular good fit, or just that communities that you've that Activeloop has penetrated well and is popular?
So yes, you have biomedical image processing, you have automotive, you have aerial imaging. There are two couple verticals that we haven't shared yet. We haven't updated the website. What we have seen from the community is that today a lot of Python developers in computer vision, especially, they have big problems with processing videos. And there are no good tools for video processing. And then the decompression I was mentioning before is like one of the core bottlenecks there. Having random access to this data instead of actually watching the video beforehand, that's another problem there. So what we have learned from the community, and it has been a target for us for earlier this year, is to focus on nailing down the video use case. And from the video use case, you actually both can impact the automotive industry. There's also like video processing, surveillance / security. That's another vertical that we have seen a lot of interest for Hub. And then aerial imaging, obviously, as we already discussed.
Yeah, it does seem like you're at an interesting point in the workflow. Like, not only are you database, but you do some of the workflow tools such that it seems like you could expand to anywhere that people are having trouble in the workflow. You can provide tooling. Like you said, video decompression is an area that you could add value, which is a neat place to be.
Yeah, if you watch Silicon Valley, the TV series, that's their core startup was, right, to build a decompression. that's
I wasn't going to bring it up, but yes, totally. Good, Davit. We're winding down our time here. Anything you wanted to cover in our show today that we didn't get to?
No, thank you very much, Eric, for hosting me and having this nice conversation. And yeah, happy to be helpful. And thanks also for our team members, to our community, to all contributors that helped us to come to the stage where we are at now. And there's a lot yet need to be done. So we are working on it.
Thanks, Davit. Super amazing progress. I appreciate your shout out to the community. I think folks can find you via your website, activeloop.ai. We'll put a link there, but it looks like you have a Slack channel.
Feel free to join slack.activeloop.ai. That basically will get it out you directly to our community. Feel free to our GitHub, go to GitHub, star us, / start using our tool. We'll love your feedback and see how we can be helpful to you.
You can find today's show notes and past episodes at contributor.fyi. Until next time, I'm Eric Anderson, and this has been Contributor.